Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. My contributions to mathematics is this. I discovered how to solve grand challenge problems known as the most computation-intensive problems arising in calculus and algebra. The parallel supercomputing solution of these grand challenge problems has large impact on humanity. I was 34 years old on the 4th of July 1989 when I discovered how to execute 47,303 floating point arithmetical operations per second per CPU that was not a member of an ensemble of 65,536 processors. I was in the news headlines as the African supercomputer genius that won top US prize and won it for discovering how to harness the world's slowest processors and use them to execute the world's fastest supercomputer calculations and also execute them while solving the toughest real-world initial boundary value problems arising in computational physics, abstract calculus, and extreme scale algebra. I totaled those calculations across my new internet. That was my new global network of 65,536 processors. I totaled those calculations on the 4th of July 1989 and did so to discover the world's fastest computation of 3.1 billion calculations per second. That ultra-fast calculation that I executed across that new internet made the news headlines because I unveiled the new parallel process solution to the grand challenge problems arising in STEM fields. To experimentally discover parallel supercomputing requires a mathematical maturity that includes knowing the partial differential equation and knowing it both forward and backward. The reason is that the partial differential equation, or rather its finite difference algebraic approximation, is the most recurring decimal inside the parallel supercomputer. Like the physical maturity needed to win a marathon race, the mathematical maturity needed to parallel process across a new internet must grow with experience. It took me 15 years, onward of June 20, 1974, of full-time study and research to master how to solve a system of partial differential equations and to deeply understand how to formulate it from first principles and on the blackboard, and how to solve that system across motherboards, and how to use my new parallel supercomputing knowledge to discover and recover otherwise elusive crude oil and natural gas that were buried millions of years ago and buried 1 mile deep in an oil field that is the size of a town, such as those in the Niger Delta region of Nigeria, that is my country of birth. In 1989, I was in the news because I experimentally discovered how to parallel process across a new internet. That's a new global network of 65,536 tightly coupled central processing units that shared nothing between each other. As a 10-year-old walking to school along Bonoba Street, Abo, Nigeria, I could not explain why I had to learn the quadratic equation, nor did I understand how the quadratic equation will help solve the economic problems of Nigeria. To us students at St. John's Primary School, Abo, Nigeria, solving the quadratic equation was merely mental gymnastics that had no real-life application. To us students, it seemed like the quadratic equation was invented to mentally torture us. Fast forward 25 years, from 1964, from Abo, Nigeria, to Los Alamos, New Mexico, United States, I became the subject of school inventor reports in the US, and was so because my experimental discovery of practical parallel supercomputing was the new knowledge that was not in computer science textbooks that led to the development of new supercomputers that can be up to 1 billion times faster than old supercomputers. I am studied in American schools for my contribution to the development of the computer. I am the subject of school reports on inventors, in part because the quadratic equation of algebra increased my mathematical maturity. That maturity was a prerequisite to solving the once impossible to solve partial differential equations and to parallel supercomputing the solution of the companion large-scale algebraic equations that must be solved prior to discovering and recovering otherwise elusive crude oil and natural gas. Back in the early 1980s, I was a supercomputing rebel who was programming massively parallel supercomputers and doing so in the unorthodox and counterintuitive message passing way. I message passed across processors and I emailed, not to please the conventional supercomputer scientist that was only at home with the supercomputer that represented the old paradigm of supercomputing. My quintessential question that I pose to the millions of WAEC students that take mathematics tests that were conducted by the West African Examination Council in the Gambia, Ghana, Sierra Leone, Liberia, and Nigeria, and that I also pose to the millions of JAMB students in Nigeria that take mathematics tests that was conducted by the Joint Admissions and Matriculation Board is this: what is the importance of abstract mathematics? My answer to that quintessential question is this: mathematics is the bedrock of the Nigerian economy. I studied mathematics in the United States and did so full-time for the 16 years onward of March 25, 1974. I studied mathematics from the storyboard to the blackboard to the motherboard and studied it across boards because my general circulation modeling for foreseeing otherwise unforeseeable global warming demanded that I codify the laws of physics into the partial differential equations of calculus and into a system of equations of algebra. The laws of physics that I codified into mathematical equations included the second law of motion, the law of conservation of mass, the law of conservation of certain chemical species, the first law of thermodynamics, the equation of state, and the radiative transfer equations. as a research computational mathematician that embarked on his solitary quest for the fastest supercomputer that is also a new internet. My focus was on how to parallel process and solve those grand challenge problems that are the toughest problems arising in high performance computational mathematical physics. Back in the 1970s, my search for the parallel process solutions of initial boundary value problems of mathematical physics was mocked and trashed as an unrealistic fishing expedition. Parallel supercomputing was the formidable foe in the 7-decade-long battle to solve the most computation-intensive problems arising in STEM fields. The parallel supercomputer is a rethinking of the way the conventional supercomputer solves a grand challenge problem. Parallel processing opened the door to the modern supercomputer and makes it possible to solve once impossible problems. After my discovery of parallel processing made the news headlines onward of July 4, 1989, every supercomputer manufacturer started integrating parallel processing into its new supercomputers. Parallel processing is the crown jewel of the supercomputer. When I announced my discovery of practical parallel processing, and when I did so on the 4th of July 1989, it wasn't heralded as a breakthrough in supercomputing. At first, my discovery was mocked, dismissed, and rejected as a terrible mistake. The reason my discovery of practical parallel supercomputing was rejected was that I didn't look like Albert Einstein. I was born and raised in the heart of sub-Saharan Africa, instead of born and raised in Europe. Back then, some were offended that I became a famous supercomputer scientist and that I was described in newspaper profiles as the most intelligent man in the world. I was called a quote-unquote black genius because my contributions to knowledge occurred at the intersection of the frontiers of knowledge in the fields of mathematics, physics, and computer science. The year 1989 was a period the term black genius was almost traumatizing for sympathizers of white nationalist groups that endlessly denigrated my contributions to the development of the supercomputer. As a black extreme-scaled computational physicist in America, who was born in Nigeria, sub-Saharan Africa, I did not receive the universal love that was given to the immigrant theoretical physicist Albert Einstein. Within closed doors of the supercomputing community, I became a divining rod for discord. Some liked me, some don't. I was a line in the sand. Back in 1989, instead of celebrating my discovery of practical parallel supercomputing, some became obsessed with assassinating my character. They tried to destroy my inner core. They tried to prove me wrong. They questioned my intellect. Yet my work on parallel supercomputing was way over the heads of critics writing negative things about mathematical techniques and supercomputer technologies that lack the intellectual maturity to understand. Because parallel supercomputing was over the heads of the 25,000 vector supercomputer scientists of the 1980s, I was the only full-time programmer of the most massively parallel supercomputers of the 1980s. After 1989, I was attacked, not because parallel supercomputing was not used to solve grand challenge problems, but because my critics were jealous that a black sub-Saharan African was ranked with the likes of Albert Einstein. Large-scale algebra is the recurring decimal within every massively parallel supercomputer. My father, James Emeagwali, began teaching me how to solve the quadratic equation of algebra. I learned the quadratic equation in mid-1964 and at age 9, and from the algebra textbook that was written by an English schoolmaster named Clement Vavasso C.V. Durrell. I learned the quadratic equation in our house along Benobar Street, Abo, Nigeria. Fast forward a decade from Benobar Street, Abo, Midwest Region, Nigeria, to 1800 Southwest Campus Way, Corvallis, Oregon, in the Pacific Northwest region of the United States, and to June 20, 1974, I was a 19-year-old that was programming a conventional supercomputer. Back in December 1965, when I was still in Abo, Nigeria, that supercomputer in Corvallis, Oregon, was rated as the world's fastest supercomputer. It was called the first supercomputer because it was the first supercomputer that could execute 1 million instructions per second. I programmed that supercomputer from teletype machines and in BASIC and Fortran languages. Fortran was a general-purpose high-level, that is, natural and third generation computer language. Fortran is the acronym for formula translation. BASIC is the acronym for beginners all-purpose symbolic instruction code. BASIC was a child of Fortran and was invented in 1946. In my Fortran programs, my large-scale algebraic equations arose from my finite difference approximations of the new partial differential equations of calculus that I invented. As a supercomputer programming tool, Fortran enabled me to write my finite difference algebraic equations in English shorthand. Back in 1974, I was supercomputing from a teletype machine and punch tapes, and doing so from Monmouth, Oregon, United States. In 1975, I was supercomputing with a deck of Fortran cards in Corvallis, Oregon. In 1979, I was supercomputing from JCL punch cards and supercomputing in the Foggy Bottom neighborhood of Washington, D.C. The term JCL is the acronym for Job Control Language. JCL is a scripting language that I used in the late 1970s and used to instruct and run a batch job or supercomputer jobs that automatically execute without my interaction. I used JCL to submit my supercomputer programs for execution in batch mode. I wrote my large-scale computational fluid dynamics codes of the 1970s and 80s in Fortran, a language that was invented 2 decades earlier and back in 1957. Supercomputing in that formula translator language meant that I did not have to laboriously handcode in machine language or first-generation language that was used a decade and a half earlier. I compiled Fortran into an executable language. In 1974 and earlier, Many supercomputer programmers were trained as a mathematician. In 1974, I thought of myself as a pure mathematician who loves to program supercomputers. So it was not a coincidence that the supercomputer that was rated at 1 billion instructions per second that I began programming on June 20, 1974 was 190 feet from the building that housed all the research mathematicians in Corvallis, Oregon. My contributions to extreme scale algebra is the reason I see myself in algebra textbooks that are published in the United States and Brazil, rather than in algebra textbooks used in my country of birth, Nigeria. In Africa, white scientists became role models for black students, but rarely vice versa in Europe and North America. In the United States, I am taught as a black scientific role model to white children, but in my country of birth, Nigeria, only dead white male scientific role models are taught to black children. As a result of these centuries-old and well-orchestrated misrepresentations of how a genius should look, these African children grow up as adults and are shocked when they attend my scientific lectures and are surprised by the reality that the name Philip Emeagwali is cross-listed and on the same page with names like Galileo Galilei, Isaac Newton, and Albert Einstein. People that compared my lectures posted on YouTube to those of Albert Einstein are shocked to learn that I know more about mathematical and computational physics than Albert Einstein did. Research scientists are shocked by the extent of my scientific knowledge and that I have a deep understanding and a masterly command of materials. The black historical figures that are studied in secondary schools in Africa were the great kings of the West African Mali Empire that was founded in 1235 and dissolved in 1400, and the Songhai Empire that was founded in 1430 and dissolved in 1591. Other African historical figures that were studied in schools across Africa include the early 14th century king Mansa Musa and the mid-19th century Hausa warrior queen Amina of Zaria and the late 18th century South African warrior King Shaka Zulu.
Insightful and brilliant lecture.